All right, so in part 2 of this video, we'll finish up this review. It says, given the definite integral from -3 to 1 of 3x squared dx, write an equivalent expression using summation notation. So this is summation notation for an integral, and you have to pretty much memorize this. If you understand what it's saying, it makes it a little bit easier. This would be b minus a over n. That's the width of each rectangle. And then its function value at a plus b minus a over nk. So I'm going to go from here. So the first part would be the limit as n goes to infinity of the summation. Okay, so that part's always the same. So then it's b minus a over n. So our interval that we're like finding the integral from would be from -3, that's the a number, and b is number 1. So 1 minus a -3 over n, and I can go and just make that as 4. And then function value, the function is 3x squared. So I say it's times 3, big open spot where x is, do squared, because where the x is, that's why I plug in that part. So it's the a number plus b minus a over n, 4 over n, k. So that would be it for this one. So this 3, if this was like a multiple choice, it'll be multiplied by the 4, but notice I can't distribute the 3 because of the square. So I would maybe rewrite it as the limit as n goes to infinity, summation blah blah blah, as 12 over n, -3 plus 4 over nk. Be ready to kind of have to manipulate that if it's a multiple choice question. All right, so the next one, the graph below shows the rate of change of the temperature of John's hot tub over 10 minutes. So the rate of change of the temperature, so that's a derivative of the total, or the temperature. So the original function, the antiderivative of this graph, would be the temperature at certain times. It says after 10 minutes, how many degrees has the temperature changed from 0 minutes? So it says temperature changed, and it looks like some of it's positive, some of it's negative. So we're going to find the area bounded by the curve, and that'll show us the net change. So it looks like it gets hotter and then it gets colder. Maybe the hot tub gets turned off or something. All right, so temperature that's the rate, so it was increasing, but I want to try to find this area above. So that looks like 1, 2 fulls, and then a third, so that was 3. And then below, looks like there's some rectangles, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 12, what, 11? I already lost count. I don't know what I'm doing. Okay, so here we go. I'll make a rectangle here, and that looks like 2, 4, 6, 8, 10. That's 10, but it'd be negative. This is half of a circle with radius 0, so pi r squared over 2. Pi over the radius, or times radius squared, so it's 1 over 2, but that's negative. And then this part is 2, but it's negative. So if I add up those, so it'd be 3 on top, so 3 minus 2 minus 10 minus pi over 2. So what is that? 3 minus 2 is 1. So -9 minus pi over 2. So the total temperature change is -9 minus pi over 2 degrees. So it went down overall. It got hotter, and then it got colder. They probably turned the heater off, and then it got cold. Or room temperature, approach room temperature. All right, so the expression, oh, this one's terrible. I'm just gonna ramble through this one and hopefully it makes sense. I did this one a couple days ago and I forgot how to do it. All right, the expression 1/8 is equal to 1/8 plus 2/8, or square root of 1/8 plus square root of 2/8 plus square root of 3/8, ... to the square root of 8/8 is a Riemann sum approximation. So it's not quite the limit as n goes to infinity, summation, k starts at 1 and goes to infinity. It's not quite that, right? Function value at a plus b minus a over nk, because there's not an infinite number of them. This doesn't say n over 8. It's just there are 8 of them. So this is a Riemann sum approximation. How many interval, or how many, what is the n number here? That's going to be the trick that helps us figure this one out. How many subintervals did we use? How many little rectangles did we divide that region up to? And it's kind of hard to tell what the region even is. So this 1/8, what is that representing, you think? So if I was to distribute this 1/8 to all of them, it's 1/8 times the square root of 1/8 plus 1/8 times the square root of 2/8 plus 1/8 times the square root of 3/8, and that goes on and on and on. And there's 8 of them to get to square root of 8/8. So each one of these, this 1/8, that is the width of each one. Because there's 8, it looks like there's 8 of them, right? It starts at 1, then 2, then 3, then 4. Whoops, that's supposed to be a highlighter. So 1, 2, 3, all the way to 8. So there's 8 subintervals. And the width of each rectangle is 1/8. So I think that can make us eliminate E. Although I'm not really liking that all of a sudden. So what is the function value that they plugged in here, right? So Riemann sums, if I had like, here's my x-axis and my y-axis. So 1, 2, 3, 4, 5, 6, 7, 8. Pretend those are supposed to be all be the same. This is 1. This is 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8. This would be 8/8, which is 1. So it's function value at 1/8, and then the width is 1/8. Then function value at 2/8, I'm just pretending it's that, and the width is 1/8. Function value at 3/8, so the function looks like it's just square root of x, right? Square root of x, and then you plug in 1/8, then 2/8, then 3/8, and 4/8, and 5/8, and it's just the integral from 0 to 1. So I split up that integral from 0 to 1, and I cut it up 8 ways. So each width is 1/8. There's your width. Whoops. And then its function value at 1/8, then 2/8, then 3/8, on and on and on and on and on. So I'm pretty sure the answer is B. And I don't think I did a very good job explaining that, but if not, we'll figure it out in class next time I see you. All right, number 6. All right, these are a little bit easier. Find capital F prime if capital F is defined to be that accumulation function. So this is testing that fundamental theorem of calculus, or the second fundamental theorem of calculus. So if I want to find the derivative of the left side, find the derivative of this, and that just means plug in sine, or that upper limit of integration in for the t. So it'd be sine x squared times the chain, which is cosine of x. That can also be written as sine squared x times cosine x. So same thing here, find the derivative. F prime is equal to the natural log of -3x times the chain of -3. Same thing on this one. F prime of x is equal to, this would be f of 7x times 7. All right, this last one we haven't talked about specifically, so let's do it now. So this one, there's a little thing we can do, is a little trick. I'm going to rewrite this as 2 separate integrals from x squared to some dummy number a where a is somewhere in between those limits of integration. And it would be of 3t minus 8 dt plus the integral from that a to x plus 8 of 3t minus 8 dt. And now we just do the same thing. With my properties, I can flip this, and I would say, I'm still just saying this is f, not f prime. Flip that, it'd be a x squared, but it's negative 3t minus 8 dt plus the integral from a to x plus 8, 3t minus 8 dt. Fundamental theorem of calculus, take the derivative of each one of them. This would be negative 3x squared, don't need those parentheses, but I put them there, times the chain, so times 2x. And this could even have been parentheses here with a bracket. That feels better to me. It wouldn't, I think it would actually make a difference. Would it have? I don't know. It's good there. I think if I put this here, the negative would still go through, and that would still, I don't think it'd make a difference, but I feel better that way. Plus, plug this in, 3x plus 8 minus 8, all that times the chain times 1, but that would be it for that one. All right, let's keep it going. Okay, number 7, it says use trapezoidal approximation with 3 subintervals to approximate the area under the curve. The curve is x squared plus 2x plus 4 on the interval 1 to 7. So usually when we're given these trapezoidal sum, Riemann sum, we're given a table. But if we're not given a table, we're going to make a table. And I wouldn't need all these numbers, all these points, but I'm just going to find all these values. This would be 1, 2, 3, 4. I'm not going to count. 1, 2, 3, 4. Okay, just make sure I got those. 10 years from now, no one's going to watch this video and it's like, why did you highlight 6, 7? All right, so what we're going to do is we're going to plug in and find function values at each one of those numbers. And I already did this. So if I plugged in 1 to the function, this is x values, this is f of x values. This would be 7, 12, 19, 28, 39. Oh my goodness. 6, 7, the last one. I hope the 2 people who watch this video think that's funny. If not, you're like, this guy's an idiot. All right, so trapezoidal sums, 3 subintervals. So the trapezoids are kind of weird. We have to remember that the area is equal to 1/2 base 1 plus base 2 times the height. And these trapezoids, so if I had like if I'm looking at my points, this is when x is 1, when x is 2, I get a height of 7 and a height of 12. So this is base 1, this is base 2, this is the height. So I'm going to look, from 1 to 7? Oh, I don't need all these, do I? So from 1 to 3, there's a number. And then from 3 to 5, and then 5 to 7. I only need 3 subintervals, so I'm going to spread them out evenly. So this would be the area. I'm not going to write area. I'm just going to start writing. So it's 1/2 base 1, which is 7, plus base 2, which is 19, times the distance between 1 to 3 is 2. Plus 1/2 base 1 is 19. Looking at this whole interval right here. Plus 39. The distance from 3 to 5 is 2. And then 39 plus 67 times 2. All right, so each one of these, the 1/2s and the 2s will cancel each other out. So what I get is 7 plus 9 plus 19 plus 39 plus 39 plus 67 is 190. That would be an approximation of the exact area under the curve using 3 trapezoids. All right, flip it over, next page. Function, so f of x is equal to the integral from a to x, h of t dt. As soon as we see this, a function that's defined to be an integral where the input is a limit of integration, the upper limit of integration, that's called an accumulation function. And I know they're going to ask me, most likely, that, I'm not going to ask me this, but I need to know that f prime is equal to h of x. Okay, we're going to come back to that. H prime is equal to h of x. This is a graph of h. What's the graph of f? So h is basically f prime. So I'm going to rewrite this as f prime, and now it's easier. If that's the derivative, what is the antiderivative? What could be the antiderivative? All right, so I noticed this has that kind of like wave like this. So it's usually like a cubic, and it maybe look like a negative cubic. So that means the antiderivative would be like a negative quartic. So something like that, exponent 4. But I don't have that whole graph necessarily, so maybe that's not helpful. If this is the derivative, if the derivative is positive, that means the graph is increasing. So I know my graph of f should be increasing from B to C. So B to C, the graph should be increasing. So those are all increasing, right? So this is increasing, then decreasing, so we can cross out A. B is increasing, and it kind of has that little, it's increasing, and then it does that, which is going to be helpful in a second. Oh, wait. B is not increasing. B's out too. That was decreasing. All right, so we're down to D, E, and C because all those graphs are increasing. All right, so if f prime is negative, it should be decreasing there. So decreasing, decreasing, decreasing. Darn, that didn't eliminate anything. All right, so but how is it decreasing or how is it increasing? Let's look at concavity. So next idea is looking at the derivative graph. If the derivative is increasing, so this derivative f prime is increasing from a little after A to a little before C. If f prime is increasing, then f is concave up. If f prime is increasing, then f double prime is greater than 0, so f is concave up. But if you look at C, it's concave down all through there. So I think C's out. This is concave down right there, so maybe. This is concave up. Oh, but we just kind of notice right here it's decreasing. F prime is decreasing as it approaches C. That means it has to be concave down right there. So that's why it's not E. The answer would be D. All right. Well, we have 2 more left. Okay. If f and g are continuous functions such that the integral from 0 to 10 of f of x is 21, the integral from 0 to 10 of 1/2 of g is 8, and the integral from 3 to 10 of f minus g is 2, what's the integral from 0 to 3 of f minus g? Okay. Well, this is weird. So I have the whole thing of f of x is 21. Let me write the dx. But the whole thing from 0 to 10 of g, if I take that 1/2 out and put it in front, this would be 8 multiplied by 2 multiplied by 2. So the whole thing from 0 to 10 of g would be 16. Okay, that's good. So if I subtract the 2, that would just be 21 minus 16, so that's 5. So the whole thing, so this would be, highlighter. So first part is this one, first part, from 0 to 3. the integral from 0 to 3, I'm going to be lazy, I'm going to say f minus g plus the integral from 3 to 10 f minus g is equal to integral from 0 to 10 of f minus g. And I'm trying to find 0 to 3. Now I got lazy, I don't have the gx, or g of x, I don't have the dx. So find that, that's going to be our question mark, or what we're solving for. This was 2, and we found this was 5. So our answer to this would be 3. All right, last couple problems. Okay, so given this graph of f, find the area under the curve, these definite integrals. So some properties. I would take out that scalar of a 2. This part right here says find the area bounded by the curve, and then multiply it by 2. Area under the curve from 0 to 1, that looks like 1 times 2, that would be 2. Okay, this one I'm going to flip it. I don't need to flip it if I'm doing the fundamental theorem of calculus, but if I'm looking at a graph, trying to find the area bounded by the curve, I have to flip the limits of integration. So from 7 to 10, that's a trapezoid. Base 1 is 3 plus base 2 is, so what's 3 plus 1 is 4. 4 times the height of 3 be 12 divided by 2, so that's what, 6. But it's above the curve, so it's positive 6, but this negative out in front of the integral makes this negative 6. Okay, the area from 0 to 7, I should probably write these in. This is 6. This was 1. So from 0 to 7, I need to find this part. So that is a circle with radius 3. So it's negative 1/2, so over 2. The radius would be 3, so 9 pi. So this one altogether would be 1 plus, or 1 minus 9 pi over 2. I'm wanting it from 1 to 7, that little area right there. All right, from 0 to 10, all of it. So was it 6 plus 1, so 7 minus 9 pi over 2. All right, 1 to 7, we just found that one is negative 9 pi over 2. And if the limits of integration are the same, it's 0. All right, thanks for watching this video. Hopefully it helped. If you have any questions next time I see you in class, make sure you ask. Bye.